we have the final generalization talk right here.
All right, so just resuming where Sasha finished off. So we're looking at some other approaches to analyzing generalization performance of prediction methods beyond just considering empirical risk minimization. So settings where we're not necessarily thinking about that sort of approach of encode our prior information into a function class and then try and find the best fit to the data in that function class. So in particular in this section I want to talk about some local methods, things like nearest neighbor methods and kernel smoothing methods, and with the intention of providing a bit of a high-level glimpse maybe of the analysis techniques for those sort of methods, which are quite different from the analysis of things like empirical risk minimization. So two things we're going to look at are k-nearest neighbor and local smoothing. And here, instead of thinking of approximation estimation trade-off, there's a different kind of bias variance decomposition. As I say, we're not fixing a class. We're relying on properties of the probability distribution, and in particular, things like if in a regression problem, if we work with quadratic loss, it's the conditional expectation that we're pursuing, and we're relying on properties of that conditional expectation, our regression function f star, it doesn't vary too rapidly as we move through the space. So maybe it has a Lipschitz property that if you only move epsilon far, then f star only moves some constant times epsilon. The intuition for these sort of local methods is that if you see a new x and you want to make a prediction there, then you go back to the data and look at what happened in the neighborhood of that x. What was the associated label for nearby points, or response for nearby points, whatever nearby means. Okay, so let's start with this bias variance kind of picture. So as before, so we have our fn hat. That's our prediction rule. You can think of it as something that given the training sample that we've seen, these x1, y1 through xn, yn, it's something that takes a new x and makes a prediction, and we're concerned with the expected loss on a new xy pair and the expectation of that. I guess we're considering across the samples, and we'd like that to be close to the Bayes optimum. So this f star is the best possible prediction rule in the sense of minimizing this loss. And we saw cases where we didn't really need to think too hard about this bias variance decomposition, the approximation estimation breakdown. We were just saying fix a class like linear functions in d dimensions, right, where n is much bigger than d, and as long as we get it, find some good fit to the data, then that generalizes. In more interesting problems, you often want to explicitly consider that trade-off. We want to think, well, actually, we'd like to be able to compete with something much more complex than just a d-dimensional thing. We might introduce a complexity hierarchy across functions, for instance, and consider the trade-off there between going for something more complex, where we get a lower bias or a smaller approximation error, at the possible expense of having bigger fluctuations, a bigger penalty for that statistical task of finding the best function in a bigger class. So this is the way we were thinking of things before. We had this approximation estimation trade-off. The approximation part is because we're picking a class and trying to find the best in the class. So this is the approximation part, and then the estimation part depends on the scale of that class. And you can think of that in a model selection sort of setting. In one of Sasha's talks, he mentioned this, where there is this more or less explicit balance between these two, trade-off between these two. We're going to look at a different kind of trade-off, a different bias variance decomposition. And it's the kind that in non-parametric statistics is totally routine. We're going to work with square loss because it's very convenient, right? So we'll get an explicit decomposition that's really nice with square loss. We're not fixing a class. We're fixing a procedure, a method, right? So it's something that typically has some tunable parameter, which is analogous to a complexity parameter for a class, but again, there's no fixed class. It's like a bandwidth parameter or a roughness of our fn hat sort of parameter. It's that's the thing to keep in mind when we mess with this particular knob. And we're interested in the trade-off that we get between bias and variance in this case. Okay, so just to remind you, in the case of square loss, the conditional expectation is the Bayes prediction rule, right? Conditional expectation of y given x. And so we can split our excess risk, right, the expected loss for whatever this method predicts versus the Bayes risk. That's the expected squared error, where this expectation is over x, y, and the sample that went into choosing fn hat. And this is the Bayes risk. We can split that up into, put an f star in here and subtract it away again. And then we get, this square term is this square term. There's this term, which is the expected squared difference of these two. And there's a cross term, but of course that goes away, right? Because we can condition on the x's, and f star of x is the conditional expectation of y given x. So, that times anything that's a function of x has an expectation of 0. Okay, so, our excess risk is just this kind of L2 distance between these two functions, the one that we predict with and the f star. And now we're going to do a bias variance decomposition looking at that kind of quantity in one more slide. Okay, not quite yet. So let's think first of all about that expression. You can think of it as, it's, as I said, it's an expectation over x here. The y's have gone away, but it's also an expectation over the sample. Writing that explicitly, here's the expectation over x, and that's you can think of that as a squared distance between fn hat and f star, and there's an expectation over the sample as well. All right, so we can often what we'll do is for this squared distance, we'll analyze that quantity, right? So we're interested in I said that badly. We're often interested in, for a fixed x, seeing what this looks like, and then saying, then what happens on average across the x's. Okay, and we use this notation L2p for that squared distance between two functions. Actually, I think we're going to drop the notation in a second and just write it as a norm squared, right? And then here's the bias variance decomposition that we're talking about in this part. So this is the quantity we care about. It's this expectation over the sample of this L2p distance between our prediction rule and the best possible. And we're going to split that up into, fn hat has some dependence on the x1 through xn and some dependence on the y1 through yn, right? We're going to pull out just what happens for these y's and consider the expectation, right, under the choice of the y. So condition on the x's and just look at the expectation under the choice of the y's of what you predict. And we're adding and subtracting that, but then we can write that as this sort of expectation, all right, again, because it's a conditional expectation, and then no other y's in sight. And so we have two terms here. All right, there's a expectation over the sample of the prediction here versus this averaged prediction, right? So if we knew the conditional distribution, right, then this is the average of those predictions. So this is a variance term. This one is just the expectation of what that averaged prediction is versus the f star. So this is a bias term, right? The best prediction would be f star, and we're doing an fn hat that maybe it varies a lot depending on what those y's are, the noise in the labels we see in the sample. This term's capturing that variance. But if we could get rid of that variance and compute the average, then this bias is looking at that piece of the puzzle. Okay, and typically, as I say, we have maybe a bandwidth parameter or something of that sort to vary, and if as we make our fn hat smoother, this term is going to go down, right? We'll have a lower variance thing, but we pay in terms of the bias because we're washing out the predictions that we should be making, and the variation in those predictions gets eliminated by having a smoother prediction rule. Typically people would choose such a parameter via cross-validation. I'm actually not going to talk at all about those kinds of choices. All right, so any questions about this bias variance decomposition? This is really central. All clear? So let's talk about these two different cases, k nearest neighbor, and we'll get on to kernel smoothing in a moment. So for k nearest neighbor, presumably everybody knows how that works, right? We're in a metric space. We're going to say, we're going to consider Euclidean norm, but all we're using is a Lipschitz property, so it doesn't matter what metric space you choose. We're going to tailor our assumption to it. So we're in this metric space, and we come up with a new x and decide how do we predict for that x. Well, here's our new x. We want to come up with a prediction based on our sample where we find, and this is our data. We find the k nearest points. Suppose k is 3, right? So we would look at the y's that were associated with these 3 closest points and predict the average of them, right? So it's 1 over k. So we use this notation, the order statistics notation, right, where x sub 1 in parentheses here means the x that's closest to little x, the test point. Okay, so this indexing, of course, depends on the test point. Okay, so this is the pair, the xy pair that's closest to our x. That's this one. And then there's the second closest, and so on. And for k nearest neighbor, we just pick the average across the k closest. Okay? All right, so that's the prediction strategy. What about these two components of our excess risk? So the variance component is considering our predictions versus the average of our predictions, under this choice of the labels in the sample. Right? So the conditional expectation given everything else. So of course, that's just the average. So the fn hat is predicting y for the closest k guys, the average of the y's for the closest k guys. The expectation of that, given the x's that we saw, is just f star, right? So every one of these, the conditional expectation of the y associated with the closest point is just f star at that x, right? F star's, the conditional expectation. We're working with squared laws. So that's really nice. The variance is controlled, and in particular goes down as we increase k. Okay, so by taking a bigger and bigger average across these closest points, if we include more and more of them, we get a smaller variance. The variance goes down like 1 over k. Okay, so the bias part, there's more work to do. The bias part is comparing this term to f star, and just thinking about it, of course, if this is averaging more and more of these k's, then we're washing out our predictions much more. So we would expect things to get worse as k gets bigger, right? We expect to be further from the right prediction. So there is this trade-off as we adjust this knob. In this case, it's k. It's the number of nearest neighbors we consider. All right. So what's the bias part look like? So that expectation, of course, is f star of xi, the ith nearest guy, versus f star of the test point. So we're considering, how does f star change as we move from the test point x to these k nearest neighbors of x. So, here we introduce an assumption. We're always going to have some sort of assumption about p in this sort of analysis. The assumption here is that f star is Lipschitz, let's say 1 Lipschitz, right? So we don't have constants floating around. So if f star is 1 Lipschitz, then we can write the squared bias, this quantity. Well, I guess first of all, there's a Jensen's inequality, and then we're saying, okay, the square of this thing, right, is bounded by the squared distance between those two because of the Lipschitz assumption, right? So if xi is nice and close to x, then the Lipschitz assumption means f star can't move very far when we move from x to xi. Okay, and so this term is nice and small. So the the bias is governed by how close these k random points are to x. And as we increase k, they're going to get further and further away. Okay, so I'm going to wave my hands a lot in the next two slides. I guess maybe not. This is actually quite precise, and then I'll wave my hands. So it turns out so what we will care about here is just how far these k nearest neighbors are from x, the test point x. So all we really need to know is how close the closest point is among some finite set of points. And the way to see that is we'll get what appears to be a sort of loose upper bound. We'll say, instead of picking the k closest points, let me take my n points, split them up into k different bins in an arbitrary way. I just fix them, the first n over k, the next n over k, and so on. And instead of picking the k closest, I'm going to pick k points that are the closest in each one of those sets. Right? So I'm doing something suboptimal here. I'm saying don't pick the k closest, pick the closest in each of those k sets in a fixed partition of the n points. Right? And certainly this gives me an upper bound. I'm not going to be, if this is the closest one in the ith bin, I'm not going to be as close as the ith closest. Fine, I'm giving something away. And then, just take an expectation. All we care about is, what is the expected squared distance to the closest point in a set of size n over k. Does that make sense?
Sorry, so you're looking at the nearest neighbors in the partition?
I'm saying instead of looking at the k nearest points, I'm going to take my set of size n and I'm going to split it up into k sets. Maybe that's one set. Maybe there's some other set down here of size n over k, some other set like this, and so on. Right? In this case, 3. And then I'm saying don't pick the k nearest neighbors and look at this quantity. Pick the nearest from, let's say, pick the nearest from each of these. So that would be that one from this element of the partition, and that one from this element, and that one. And I'm saying if we do that, rather suboptimal thing, we get an upper bound. We're not making it any better, right? Because these were the nearest.
The partition is not geometric, it's on the list.
Partition is just whatever fixed thing I want to do. Let's say the first n over k, the second n over k in the sequence 1 to n. So nothing to do with the ordering of distances or anything. It's a priori fixed. And then we just need to consider the expectation, but of course for each of these it's just pick a set of size n over k and look at how far the closest is. Yeah?
Does the number of particles need to be constant for each prediction you do further down the line? So the n will remain constant, or that can also change?
N will remain constant.
So if you have n particles and you fit them as they want.
Right.
So if we go to the next step, and will that n will remain constant, or that can change also?
So here we're considering n as a fixed thing. K is this parameter of our k nearest neighbor method. These are fixed. And I guess I'm assuming that these bins have all the same size. It's no big deal if one of them's a little less than n over k, but right?
Thank you.
Was that a question? No. Okay, so this is just to simplify our problem, right? It means we only need to care about the expected squared distance between x and the closest point in a random set of size n over k. We just need to pick that one closest point. So we're getting away from the k nearest neighbors to just what's the one nearest neighbor. And that's something, this is where I wave my hands. If the support is bounded and we're in a high enough dimension, then we get the expected squared distance from a point from a particular distribution and the closest point from the same distribution. That expected squared distance goes down like the number of points we're considering. I wrote it as n here, to the power minus 2 over d. Right, so squared distance, so distance is like n to the minus 1 over d. So this is bounded support. We're making another assumption about p, right? And you can get an upper bound of this sort. I mean, this is kind of terrible, right? It's a terrible rate. This is 1 over n to the 1 over d. As d gets large, this is very, very slow. But equally, we're making a very weak assumption, just that f star is Lipschitz. And so, I said n here for a set of, this is the closest point in a set of size n, so we have sets of size n over k, so this thing goes down like n over k to the minus 2 over d, and plugging that together with the bias, plugging these two terms together, the bias and the variance together, we get the variance goes down as k increases and the bias goes up as k increases. And if you pick the right choice to optimize this bound at least, then the combination of the two looks like n to the minus 2 over 2 plus d. And then we just integrate across x's to say that the expected squared distance, which is equal to the quantity we care about, right? The excess prediction risk for this k nearest neighbor method above the optimal goes down like n to the minus 2 over 2 plus d. Questions? Yeah.
Can we improve the bound if we choose the k nearest, kind of k nearest points?
You mean rather than this sort of analysis? No, I think you get this is the right rate. Yeah, this is optimal. So, we didn't lose very much by splitting it into these sets in an arbitrary way and picking the closest. So if we introduce other assumptions about the probability distribution, we can get faster rates. If you're willing to assume more about f star.
And if you make assumption about derivative being Lipschitz, you also cannot improve much?
So no, you get a faster rate in that case. I mean, I actually don't know the details, but I know that you can get the number of derivatives that you have bounded in this way appearing in the exponent, and I don't remember these things. Maybe Sasha, do you remember the couple of sort of results?
D over r. No?
It's n to the minus.
Divided by 2t plus s.
Is it d over 2?
It's 2s by 2s plus d. So
Thank you. Great. S plus d, and we had s equals 1. Thank you. All right. Other questions? Yeah.
If you use like some sort of projection method, can you drop or reduce the dependence on that dimension?
If you use some sort of projection method, can you? So these are minimax optimal rates for under these assumptions. So if you're willing to assume you have this many derivatives bounded, then it's n to the minus this many, and there's no possibility there are upper and lower bounds. So the answer is no under these assumptions. All right. So the other case. All right. So with an appropriate choice of k, and we saw that depended on n, and it depended on if we look at a more refined result, depends on the sort of degree of smoothness that we're willing to assume. This sort of analysis, where we're making an assumption about the probability distribution and, then studying this bias variance decomposition for this specific method, it's very different from thinking about empirical risk minimization over some class of functions and, how close expectations are to sample averages and so on. It really is an analysis that's peculiar to the sort of local nature of this sort of prediction method. So there was a compact support assumption on the x marginals, and then this Lipschitz assumption on the conditional distribution. These are the things the assumptions we needed to make things work for this analysis. All right, so moving on to the other example I wanted to cover. This is a local kernel regression, so kernel smoothing kind of approach. So again, it's local. We're using the data that we've seen in a neighborhood of the test point to make predictions about that test point. So this is the Nadaraya-Watson estimate. So we fix a kernel. Maybe it's one of these functions. we're going to assume that there's a sort of bounded support for this kernel. So, so things that you might want to do like an exponential, a Gaussian kind of a thing, let's just truncate it, right? So it makes very little difference if we truncate it far enough away, but this is an assumption that we'll use for the analysis. Or maybe, you want to consider some other kind of kernel. And this is the way that we weight nearby points. Right? So in this case, the parameter that we have to play with is a bandwidth parameter. It's varying how wide this shape is, varying the scaling on the x. So we consider this fixed kernel function evaluated at x scaled by h. Right? So if h is very large, we have a very pointy kernel. If it's small, I said that backwards, right? If h is very large, we have a very smooth k sub h, and if it's small, we have a very, very tightly concentrated thing. Okay, and so this thing is 0 outside h, right? If you're considering, so the way things are going to work is we're going to use this as a weighting function about every point we saw in the sample. And so if we're further than h from that point, it's going to have no impact at all. Okay. Okay, and actually the other assumption we're going to make is just that these k's are also bounded from below. And we'll see where this kind of thing slips into the analysis too. Okay, so what does the estimator look like? Well, so we have our xi's, whatever they look like, and each one has an associated yi. And then we're considering this estimate, which is a weighted sum. The weighting depends on the test point x, so let's put our x in here. The weighting depends on that test point x, and it gives us the weight associated with each of the yi's. So here are a few x's. Right, and the weight is we place a kernel around. I should have done this in one dimension. So let's simplify. Right, we place a kernel around our training sample. So we have, maybe this is x. This is an x here. There's another one here, and another one over here. And our kernel is something that looks like, one of these functions, whatever, something like that, right? So it's this thing and this thing and this thing, and this is not a very interesting case, right? So it's only x2 that plays any role here because all of the others are more than h away from x, right? But if we had several of them with this non-zero, then we'd be taking the weighted average of the label associated with the many of them. So suppose we had a bigger value of h, then we might look at something like this, and this, and this, and then we'd be taking an average of these two y's, and the average depends on the value of the kernel at this test point here, right? We get a weighted average according to the values here. All right, so this is a number between 0 and 1. Right, that gives us how much attention, that tells us how much attention we're paying to the y associated with that particular xi. Okay? Is that clear? Do you like my artwork? Okay, so here the bias is nice and easy to estimate. So the conditional expectation of our predictions when we average over these y's and fix everything else, right? We're just taking the expectation of these y's weighted according to the x. Well, that's just f star at the xi times the weight that we associate with that xi for the test point x. Okay. And so if we subtract f star, this is a convex combination of the f star xi's. Right, and And so we could think of it as a convex combination of the differences between f star at xi and f star at x, what we should have predicted, or the ideal prediction. Okay, and you know, this makes our life very easy to make this assumption that the support is bounded by h. You know, this thing is going to have a weight of 0 if x is more than h from x star. X, the test point, is more than h from xi, I should have said. Right, so if we're outside a radius of h, right, then we don't see, then we get a 0 weight. And so the biggest difference that f star can have in here between a point x and a point xi that's no more than h away is h, because it's a one Lipschitz function. So it's h squared is the biggest squared value of this thing that we can see. All clear? Okay, so that's the bias. What about the variance? So here we're looking at, this is the conditional expectation where we're given everything except the y's, and this is our actual prediction, and we want to know what's the expected squared difference. So let's look at this difference. You know, these guys are the weighted yi's, right? Weighted according to how far x is from that xi, and the expectation here is the weighted f stars. Okay, so we can take the expectation of the square of that quantity, and you know, again, the cross terms are 0. When we take the expectation of this, we get that. Conditional expectation given the xi. And so, you know, this is what it looks like. And so we're left with thinking about, you know, the weighting squared in this sum. Okay, so what is that sort of expectation going to look like? You know, the conditional expectation of this thing is just whatever it is, right? It's some constant. So all we really care about is this quantity. Okay, so you know, again, wave my hands here, so that under some assumptions on the density of the marginal density of the x's, we get something. We get that this ratio looks like something order of 1 over n times h to the d, where d is the dimension. And when we plug that in, right, we get, for again an appropriate choice of h, this bandwidth parameter, we get a sum of two terms is like n to the minus 2 over 2 plus d, all right, which is the same rate we saw in the nearest neighbor case. Okay, so two different cases where we've got this sort of smoothness parameter, k, the number of nearest neighbors, and h, the bandwidth of these kernel smoothing estimators. All right.
Excuse me, why wouldn't kernel smoothing give you a better estimate? It looks like it's a better thing to do, right?
Maybe, but they're both minimax, you know, under this assumption. Right, so you can't hope to get a better estimate without any more assumptions than just the Lipschitz one, and you know, some density assumptions that were kind of, I guess, convenience. The marginal distribution on x, I guess, is not, you know, is not something to focus on, at least here. So you know, maybe it seems more, it seems like it should be a better estimate. Turns out that's not the case under these assumptions. We're getting the same rates. Yeah?
So I guess, strictly speaking, it's asymptotically minimax, right?
That's right. This is all rates. This is talking about rates and not saying anything about constants. It's saying what's the rate as n increases, the rate at which you can hope to approximate the square difference between your prediction and f star of x. Right. Is that what you meant?
Yeah, just towards what people experience in building analysis.
I see.
You might.
Right. I mean, you know, is the world adversarial in its choice of probability distribution. That's what minimax means, right? Under these assumptions, pick the worst for your estimator. Yeah. Yeah, that's a good point. Other questions? Okay. So, all right. So that's all I wanted to say about those kinds of smoothing methods. The last part is all about a phenomenon that really has emerged from deep neural network practice. That I think is really pretty fascinating from the theoretical point of view. Again, seems like it's far from the kind of approach where the style of analysis of empirical risk minimization, where we consider deviations between expectations and sample averages for some class of functions, seems like we're far from that world with this phenomenon of interpolation. So the observation is this, that in practice people seem to train deep networks to zero training error, and we saw in Sasha's talk this morning that situation for classification, but here the same can be said for a regression loss, like squared error, right? So if you train a deep network or anything to have zero regression loss, zero squared error, you're getting it exactly right on every training example, right? There's no more there's nothing more you can do for that training set. So there's no notion of a trade-off between fit to the data and complexity, right? You can't trade two things off if you're doing the absolute best you can with one of them. Okay, so that's a strange thing, but I guess the really surprising thing is you get good performance out of this. So this is something that a lot of people were talking about there was a Simons Institute program on foundations of machine learning 2 years ago, and in the boot camp, Russ Salakutinov was talking about, here's an approach that people use in practice. You have a data set, you come up with a network, use the data set to choose parameters of that network with stochastic gradient method. If you can't get to zero training error, you pick a bigger network, right? Until you've got an architecture that's powerful enough to get things exactly right on the training data. This sounds like madness, but it turns out, you can get, and then the rest of the story was, and then you back off a little in some sense, add in a little regularization or something else, and you get some slight improvements that way. The really striking thing is they're slight improvements, right? You're actually doing really well by having zero regression loss with this sort of optimization procedure. So a lot of people were talking about it at that program. Soon after that, Ben Recht came and gave a talk, which was actually, you had to dig down to find the same phenomenon in this paper. That's a widely known paper by a bunch of folks at Google, where their emphasis was on this fact that you can actually fit a rather arbitrary training set into a neural net, a standard neural net architecture, without that much effort. And they showed this is time to overfit for different training examples. One of the striking things was you could even give random labels to the data. This was for a CIFAR 10 data set. It's not written anywhere. But you could even give random labels, randomly choosing, say, 50% or 100% of the labels. And you can still find parameters of the network with stochastic gradient descent that fit that perfectly. All right, and it's a bit more effort when you have totally random labels than when you have the actual image labels, but it's possible to do. And the other thing that you see is that as the proportion of noise increases, of added noise, I should say. I mean, it's CIFAR 10, so it's not such a crisp, easy to label data set. But as this proportion of added noise gets increased, the performance degrades, right? Now, the thing that's not stated anywhere in the paper, and you have to talk to the authors, this test error, this is classification loss, right? The training error that they talked about for overfitting. Overfitting here means getting a perfect fit. They were also talking about classification loss, but in fact, I don't know for that graph, but in fact, they were observing this sort of performance when it was regression loss as well that was going to 0. So, that's a really striking thing. You know that you've injected noise into the problem, right? You're then coming up with 0 regression loss, so fitting the labels exactly, these noisy labels exactly, and you're still getting pretty good performance when you do that. Okay, so that's extraordinary. You're taking that noise and putting it into the parameter somewhere in a way that doesn't seem to hurt. Okay, and the other thing is you've got 0 regression loss, so there's no trade-off between performance on the data and whatever notion of complexity you care to define. So it's certainly overfitting. There's no better fitting than to interpolate every data point, but it seems to be benign. Okay, so stepping back from that, I do want to emphasize, there are some things that are not so surprising about this observation, and some things that I think really are, or one thing that really is surprising. It's not so surprising that there are more parameters than sample size. Okay, that's what the statisticians call non-parametric. That's not a big deal. I mean, maybe it's a big deal in that there's no explicit effort to keep control of complexity in this non-parametric setting, but there are certainly implicit efforts if you're doing stochastic gradient descent. We're going to hear all about implicit regularization of this sort from Nati later in the boot camp. So that's not so extraordinary, of course. Getting good performance, I don't know, I guess, right? Getting good performance with 0 classification loss, there might be something else going on, hidden by the fact that classification loss is ignoring a lot of detail, right? It may be that there's a regression loss that's actually being traded off against complexity underneath, right? If you don't threshold things and look at the regression loss, there's at least room for something to be going on there, and this is a phenomenon that as we heard in Sasha's talk, people have been thinking about for decades now. The other thing that's not surprising is if you get 0 regression loss and it's a problem that has no noise, right? So the perceptron example we saw right at the beginning is exactly that flavor. It didn't just have no noise; it had a big margin, right? Okay, if there is a function in your class of functions, if you want to think of it that way, that gets things absolutely right, so there's no noise in the problem, then a perfect fit to the data is totally fine, right? So the thing that is really surprising in all this is we're getting good performance with 0 regression loss when there's noisy training data. So you're taking all the noise in those labels, pushing it into the parameters, and hoping it doesn't hurt. And turns out it doesn't hurt the prediction accuracy. So I think that's something really striking. It's, to my mind, this is a new phenomenon that has emerged from deep learning. Okay, so this is just to look at the kind of established wisdom about fitting a data set perfectly. So, sorry.
How does it compare with the same observations for adaboost, like both fitting the random labels and fitting the data on lots of cases, not all, but perfectly and improving beyond that.
Right. So adaboost is minimizing this regression loss. It's not getting that to 0. Right. In many of these examples that we saw, the exponential loss that we saw this morning, this e to the minus y times f of x, that's the regression loss that arises there. That's what adaboost is actually minimizing. It's the convex loss. That's something that's not going to 0 unless you have a 0 noise kind of problem.
But I mean, in deep neural nets, if you actually look at the cross entropy loss, it's also not going to 0. Either means close to 0.
Yeah. Right. So I guess there's 0 and there's 0. You mean getting very small values versus taking taking parameters off to infinity to get 0 values.
So you're saying that the regression setting is maybe more. So.
Yeah, right. Okay, so I mean, I guess there's more going on. If you need to take parameters to infinity to get an actual interpolating solution, then that's a little different from a loss like a quadratic loss, where you can with finite parameters get things to go to 0.
Yeah.
Right. Nati.
I think in boosting you are getting, so in the examples of boosting, because there's at least what Sasha, I think, showed before, and I think I'll show it again tomorrow.
Right.
I mean, for your experiments in boosting, you are getting definitely going to 0 loss, because you're going to 0 training error, and once you have 0 training error, the x plus will go to 0.
I can show you the plots. Let's do that.
So, and I think that a similar phenomena is actually happening there, although it was, in retrospect, maybe overlooked, because you're not getting.
So if we look at this plot,
Right.
Nope, next slide. It's a little small, isn't it? All right, so we're getting this distribution of the margins as, that's why it's so fuzzy. There we go. Hey, I was focused. So in this plot, this is the margin distribution after 5 iterations. Here's after 100. Here's after 1,000, right? And the difference between 100 and 1,000 is really very small. This is on a letter data set, and the exponential loss is small here, but it's certainly not going to 0.
It is going to 0. It's definitely going to 0, because what you're right that, I mean, we'll talk about it more tomorrow, but it's
okay.
The things that's going to 0 only at a rate of 1 over log t, so we'll see tomorrow, which is why it's barely making progress.
Oh, I'm looking at the margin distribution here. I see.
Yeah, but the thing is, it's definitely going to 0 because you're separable, right? So you have 0 classification error, and you're doing coordinate, what you're doing.
Right, that's right. You're right.
So you're definitely going to 0.
Yeah, but yes. Okay. Okay, good. So actually, the same phenomenon is here, is present here.
Right.
Good. That's good. Yeah. You notice I was cautious when I was showing the classification side, saying there's still room for this particular thing. So that's good. Okay. That's a good point. So and I guess you're going to talk about those sort of asymptotics for.
I will talk. I mean, what else? I will talk tomorrow about the fact that it goes to 0 and what happens there. But I think the issue with the interpolation learning, I think it's. Okay, so actually, maybe I should phrase this as a question. It seems to me that it's fair to say that actually it also exists in boosting, except it was not really.
Certainly wasn't studied.
It wasn't studied and wasn't paid attention to.
Right.
Right. I think it was.
So maybe this isn't a contribution that deep learning practice has given us, but
it was studied, but people settled on margin, even though there was some paper saying, "Oh, actually, it's not quite enough," but it wasn't didn't reach the attention of the masses.
Good.
We're opening the grave now.
We will.
Good. In any case, the point I really wanted to make was not a historical one so much as this is a phenomenon that I think is really important and really interesting, and really. So maybe I should remove the second dot point in this one, and just showing just how ingrained this view is in kind of the statistical mindset, at least. This is the Hasty, Tibshirani, Friedman book. It has things like interpolating fits are unlikely to predict future data well at all. With too much fitting, bad things happen, and so on. You see it in many places. Something that interpolates the data, hence, is not a reasonable estimate. So, okay, so this is I think a really important and interesting phenomenon that training these kinds of prediction rules to fit noisy data perfectly still leads to good predictions. Okay, so it's not isolated to neural nets. This is an example from a paper of Sasha's looking at kernel regression on a digit classification problem. And you see that as you, in a kernel regression problem, you have a regularization parameter that tells you how much the norm of the the norm in the Hilbert space of your prediction rule gets taken account of in a trade-off between that and the fit to the data. And as you take this lambda down to 0, that corresponds to ignoring the regularization, right? And as you approach 0, you're seeing the test error here is getting much better, and this is on a log scale. Things are only improving as that regularization parameter gets small. Well, this is difficult to see even after I put it up to full screen. On the x-axis is the number of training iterations, again for a linear problem. This is a kernel regression problem, and they're getting, as we move for many of these, these are each different data sets. As we move to the right, we're seeing training error. The red lines go to essentially 0 in all these cases, and the test error is improving. We're certainly not seeing this decrease and an increase. We're not seeing any evidence that things are performing poorly as we get this better and better fit to the data. In many cases on the right-hand side, it's an interpolating fit. And these are I'll say descent methods. It's not gradient descent in many of these plots. So we should be thinking of it as this training progresses, we're doing less and less regularization. There's this close correspondence between the how far you've gone in a gradient descent and some notion of the scale of the prediction rule that you end up with. Okay, so I want to look at a few 3 examples. So how long do I have? 25 minutes. So I want to look at 3 examples where we can say something about interpolation. Something about performance in this sort of setting. So one nearest neighbor is an interpolating prediction rule. It just doesn't happen to have a small excess risk, right? I guess this 2 can be improved, but it's still a constant in any fixed dimension. It's back in the 60s, Cover and Hart showed that one nearest neighbor has this sort of a guarantee. So if the Bayes risk is nice and small, then one nearest neighbor is going to do well. So the noise-free case. Right? But when there's noise, this particular interpolating prediction rule doesn't have its risk approaching the optimal. Right? You're suffering from interpolating the noisy labels. But there's this work of Daniel, who's here somewhere, hiding over here. Daniel and collaborators, Berkeley and Mitra, on a variant of one nearest neighbor. And the way this works is to take a sort of a simplicial partition of space defined by the sample. So one nearest neighbor, you might have three neighbors close to a point here, and you would consider the closest one. In this simplicial nearest neighbor, simplicial interpolation scheme, they take this partition, so partition the space into simplices. So in 2 dimensions, you look at the 3 points whose convex hull you're contained in, the test point is contained in. You're partitioning the space according to all of these simplices, and then you're predicting using the generators of the convex hull that you're in, right? So if I'm here and these are the three points in this simplicial partition, then I'm going to predict using the labels associated with those points. But I don't just pick the nearest neighbor's label. I pick the linear function defined by those 3, or those d plus 1 in d dimensions. Okay, which has the nice property that at any one of these points, at any point in the sample, I'm actually interpolating, right? The linear function, of course, goes through the values at those points. So it is an interpolating prediction scheme. The nice thing is that under some assumptions, you can show that excess risk, or equivalently, this is again in the squared error case, the expectation of the difference between the squared difference between our prediction under this scheme and the Bayes rules prediction goes down like, there's a variance term, just think of that as a constant, times a constant over d, right? Something like 1 over d, excuse me. So somehow in high dimensions, you're getting something that's closer and closer to optimal as the dimension goes up. Right? I mean, it's not telling you that for any fixed dimension you'll approach the optimal performance of f star, but as the dimension gets larger, you'll do better and better. And the intuition, I guess, is that for this sort of interpolation, compared to nearest neighbor has some very significant fraction of this simplex where it's deciding to predict according to this guy's label. Whereas this simplicial interpolation, it's doing the linear function, but it's, if you think about it as being, what's the impact of a noisy point, a bad label on this thing compared to what the f star would look like, which is in some sense the average of the nearby labels. In high dimensions, that impact is small, and it's sort of a 1 over d kind of fraction. Okay. The second approach I want to talk about is local kernel smoothing. So this is Sasha's work with Misha Belkin and Sasha Sivakov. So this is looking at, again, these Nadaraya-Watson kernel smoothing kinds of estimates. But instead of using something that looks like that is bounded, they consider these crazy kernels that go to infinity at the data points, right? So at these xi's, they look at kernels that go like 1 over the distance to xi. So, so we have this singularity at this point xi. And thing goes off to infinity like 1 over the norm to some power. And if you think about what that weighted sum looks like, right? You're making your forecast according to yi times wi of x, which for your test point is saying, what's this kernel look like centered at xi for my test point x, and dividing that by the sum of these wix's. Okay, so you get a proportion of the yi's. But if we make this wi go to infinity at the data point xi, then as x passes through xi, that one dominates. And we get exactly yi. We get an interpolating prediction. Right?
That should be a min. I'm sorry.
Min of that, yeah. I wasn't even referring to it, but yes. Should be a min, typo.
So if it's min, it doesn't go to infinity?
This doesn't go to infinity, yeah. But, the analysis that we saw before, ignore clipping it. Just think about this thing that actually goes to infinity, and then the weighted sum, really does emphasize only the one the point that you're at. When x is at xi, you predict just yi. So you get an interpolating solution. Depending on the bandwidth that you choose, you might move very rapidly away from that interpolating solution, but still you're getting an f hat that passes through yi at every xi. And if you think through the argument that we gave, it still goes through. So actually memorizing the data doesn't harm that sort of bias-variance trade-off argument. And this paper showed actually that if you choose the bandwidth appropriately, you can still get these min-max rates. Okay, so I think it feels like a very unnatural kind of interpolating prediction strategy here using these kernels. They seem like a bit of a curiosity, but it's certainly a demonstration that you can interpolate and still get good statistical performance out of it. You know, I mean, maybe it's worth being cautious about that, right? I could come up with an interpolating prediction rule that performs well by giving you a standard RKHS kind of scheme and then saying, oh, but it's a two-step process. First of all, I'll check if x equals one of the xi's and then return yi. Otherwise, I'll give you the prediction that my kernel method gives you. It's not so interesting, right? It's an interpolating prediction method, but feels a little unnatural.
Quick question. So the dimension here doesn't enter?
I'm sorry?
In this part, nearest neighbor, the dimension was blessing here.
Oh, yeah. So here, that's right. That's right. The dimension, you know, so this result is saying, you know, we actually don't approach f star, but we get close to it, particularly if d is very big. Yeah. So this is a weaker result. This one says, you know, we do. I haven't written it down anywhere, but you know, the result that was given about the analysis of these kernel smoothing estimates, you know, the same style of analysis goes through, so you're getting this the dimension appears in the rates, right? Because we're making this particular Lipschitz assumption. Yeah, but you know, it's not like there's a gap between the performance, as there is here. You know, there's a gap between your performance and the optimal performance in this case. That's not true. You can get the optimal, you know, the index optimal rates, for instance. Certainly, asymptotically, you get the excess risk going to 0. Other questions? All right. So I want to say a bit about two pieces of work on linear regression. So this is you can think of it as being in Hilbert space. To start with, think of it as a reproducing kernel Hilbert space and doing a minimum norm interpolation. So, you know, if we're in one of these settings where we have the freedom to interpolate the data to get everything right, then of course there are typically many solutions that are possible, right? And the lower bounds from the talk that Sasha gave show us that. Actually, yeah, and I guess my talk show that you know, you can certainly find solutions that will perform very badly, right? But you know, so we need to specify a particular interpolating solution. So let's pick the one that has the smallest norm in the first case in the RKHS, and so it's you know, in some sense in precisely this sense the smoothest, the minimal. Interpolating solution, and you know, you can write it in a closed form way in terms of a kernel matrix. This is the empirical, the Gram matrix, right? The matrix of inner products between the points in the training set. Take the inverse of that times this is the vector of labels, and then this is the vector of inner products between the test point x and the training data. Those are the predictions you're making when you want to do this minimum norm interpolation, and working with a gradient flow gives you something that's really close to this minimum norm solution asymptotically. Okay, so we're going to consider that case, and this is Sasha's work with Teng Nguyen Liang. So the case they were considering was a kernel had the form, you know, k of uv was some function of the inner product between u and v. This is a Euclidean inner product, so you know, maybe this is like a polynomial or something, but it's some function that has some curvature, right? So kernels of this form, and these uv's are from Rd, right? And then, you know, under some properties of the way this X is the matrix of data in the d-dimensional space. So you know, when you know something about the way that data lies, if d is large, if the phi has a nice curvature, then you can get bounds on the performance of this interpolated solution, where the interesting term is this bias term that depends on an effective dimension. The effective dimension looks like, you know, this is the sum across the d dimensions in the input space of eigenvalues of this matrix, right? So this is the Gram matrix, right? Divided by the same thing plus a gamma where the gamma appears in the curvature of this phi. So it's sort of a parameter of the problem that arises from the kernel. They're in this specific regime where they can apply random matrix theory results, where the dimension d here and the sample size are going to infinity in some sense together. You know, asymptotically they're like a constant factor apart. Alex?
So this is zero initialization. The generalization became crucial in...
Yes, if you want to think of it as doing gradient descent, it is. But you know, actually the analysis is all about this explicit closed form solution for the linear case. You know, we know how to solve least squares problems. It's x transpose x to the minus 1, x transpose y. Right? This is the kernel form of that.
I see. So
But we want a minimum norm solution. That's not something we can invert. So we say x transpose x pseudo inverse x transpose y, and that's exactly what we look at. And what's analyzed in Sasha's paper here. If you want to think about it as what happens here, to get that minimum norm solution, then yes, you should start at 0. Okay, and you know, this has some nice parallels to what goes on when you think about the ridge regression, right? You get a very similar kind of effective dimension arising in a ridge regression problem where this lambda is the regularization parameter in your ridge regression, where you say, you know, I want to minimize the squared error plus lambda times the L2 norm squared of my parameters. That lambda appears there, and you're getting, you know, something that might be smaller than the dimension. Okay. And I guess so things depend on properties of the empirical kernel matrix. The eigenvalues of the empirical kernel matrix appeared, not empirical kernel matrix, this Gram matrix in the input space on that previous slide. And then in terms of what actually happens for a particular situation when you have some information about the population, you know, what does the covariance matrix look like for these vectors in D space? You know, these are some experiments that these guys did where, you know, if you have the eigenvalues of the covariance matrix before you put it through this transformation going decreasing at certain rates, then, you know, different things happen. There seems to be an optimal value. If things decrease too fast, it's not good. If they decrease too slow, it's not good. And in between, it's somehow better. I think it's not totally clear, you know, what's going on, what you can conclude about the empirical Gram matrix and its impact on the problem under these sort of assumptions on the data. But is that good?
Yeah.
So yeah. All right. Questions? Yeah, Dan.
So, so I remember, if I remember the analysis, it's in looking at L2 risk, and I'm wondering, like, is that that's not when I think about the failure that could potentially happen with interpolation, I guess I think our intuition is more visually about L infinity, right, than it is maybe about L2.
You know, noise is noise. You're taking the noise from the labels and you're putting it into your estimate of these parameters. So it's what you know, still in L2 that you expect that to be a harmful thing.
Yeah, right?
No,
yeah,
but
it's still surprising.
Anyway.
You cannot hope to get L infinity a consistent solution because you go through the noise, so that's a constant gap. Right?
Yeah, of course. But I guess I'm defending L2 rather than of course.
Yeah.
Of course.
Well, I mean,
rather than attacking L infinity.
Yeah. And then also, you know, when we think about when people draw pictures of interpolating solutions, and all the book pictures you gave were one dimension. In high dimensions, your data points are maybe very far away,
right.
and then the active interpolating isn't quite so absurd.
Yeah, isn't so absurd, and I think that's the message from, you know, this work that Daniel did on the simplicial interpolation.
Yeah.
Yeah. In high dimensions, it's not so. It's not so crazy. That's a good point. Okay. Oh, yeah.
So should we think of overparameterization as a way that like all these parameters are just learning the noise, and some others are learning the real?
Let me get onto that. So I think that's a really good way of thinking of it. So also Sasha has with a student some lower bounds for a specific kernel that says that I guess bottom line is you can't hope to do anything unless you're, in general anyway, for this sort of kernel, you can't hope to do anything unless you're in a high dimensional setting when you're working with this sort of a kernel interpolating scheme. Did you want to add anything?
Yeah, but this is exactly this thing that in high dimensions things are more forgiving.
Right.
It's the same,
right. In high dimensions, you pay less. The one-dimensional picture is misrepresenting things, that the interpolating points are not so crazy as the dimension gets higher. On the other hand, for any constant dimension, this is bad. It's a constant. Okay, and the connection to neural networks, I'd hoped to be able to skip through this and say you saw all these definitions in Jason's talk this morning, but then Jason didn't oblige, and he's going to talk about this tomorrow. So I'm just going to skip over it and say, look out tomorrow for a particular kernel that appears in the setting of random initialization with very wide networks, wider than the sample size. You don't have to move very far, and so you can think of the linearization as essentially all you can compute with a stochastic gradient sort of method. Right, so there is, think of that linearization as, it's defining a class of linear functions. That's the bottom line. I don't need to go through the details of that. See Jason's talk tomorrow. Okay, the last thing I wanted to talk about in the last 5 minutes. This is work that I've done with Phil Longaber-Lugosi and Alexander Ziegler, who's somewhere in the audience over here. So this is looking at linear regression. Let's think of it as finite dimensional. It's true in Hilbert space as well. Let's say Gaussian. It makes the makes everything more convenient, but I think we can get everything to go through for the sub-Gaussian case. But just think about x, y jointly Gaussian means 0. Then the parameters of our linear regression problem are the covariance matrix of our x's, and in particular, their eigenvalues. Right? So think of the lambda i's as a decreasing sequence of eigenvalues. That's all the information we need because everything is sort of direction independent. We can work with whatever basis we like. So it's just the eigenvalues that matter. There's a theta star. There's a least squares parameter vector. And all we really use about that is that it's got a finite norm. And there's some level of noise. Right, and it's positive, so we're not talking about the sort of easy zero noise case. Our estimator is the interpolating one, so we're thinking of the case where actually lambda n is bigger than 0, so we can find an interpolating solution, right? And the least squares solution, this is solving the least squares problem at minimum norm. We're taking the pseudo inverse of x transpose x and multiplying that by x transpose y. So it solves this least squares. Think of it as minimum norm such that you solve the least squares problem, but we're interested in the case where that solution to the least squares problem is 0. We're interpolating everything, so we need to have enough of these directions. So we're asking when can the label noise be hidden in the parameter estimates without hurting predictive accuracy? And of course, this is the quantity we care about, L theta hat minus, I'm writing theta hat rather than our Fn hat, minus L star. So it's this excess prediction risk, and of course it depends just on how far we are from the least squares parameter vector. Weighted, the directions are weighted according to these lambdas, right? That's one role that the covariance matrix plays. It's telling us how much an error in a parameter estimate in a direction in parameter space affects predictive accuracy. So here's the theorem. There are universal constants so that for any linear regression problem, we need to have theta star bounded norm, so the least square solution, is finite. Noise level and our covariance matrix, this is where all the action happens. We want to be able to interpolate. Then you can say the expected excess prediction risk, the expected excess risk is bounded above and below. There's a term here that's just the classical term about getting the signal right? Getting the theta star to be accurately approximated by our theta hat. That's more standard. This term, and in the lower bound also, is where all the action is. This is the impact of the noise on the parameters. And we get upper and lower bounds, so this is exactly what's going on. What do these things mean? Well, there's a noise level. They differ by constants. There are two terms, k star over n and n over some notion of effective rank. And the k star is defined in terms of some other notion of effective rank. So let me explain what...
So the getting the signal right part, is it only in the upper bound or also in the lower?
It's only in the upper bound. I mean, presumably, yeah, I guess we haven't tried very hard in getting that into the lower bound. That's the, in some sense, less interesting part, right? If you do this Biasvariance decomposition, this is the part that tells you how much error do you get from the theta star transpose x part of the labels, and the other part is telling you how much error do you get from the noise. Okay, so k star is how many dimensions you have to go through before the effective rank of the orthogonal subspace is bigger than something like n. And I'll say what that means. And then up here we need this effective rank to be big compared to n if you want that quantity to be small. So what are these effective ranks? They're saying ignore everything up to k dimensions, the highest variance directions. And beyond there, look at the L1 norm of the eigenvalues in that subspace divided by the biggest of them, the L infinity norm. And this capital R is looking at the L1 norm squared divided by the L2 norm squared. Right, so it's just like, if you think about, let me give an example. If you're in finite dimensions, right, then it's rank times some notion of symmetry. Right, so in the two cases, they're different notions of symmetry, but these S quantities, S and capital S, lie between 1 over P and 1. Right? 1 over P is when you really only have one direction where anything's happening, and 1 is where things are spherical. So it's sort of, if you're very symmetric, then it's just the rank. If you're very asymmetric, then it could be much smaller than that. In particular, you can go off to infinity, and it's kind of looking at the effective rank in that sense. Okay, so if we go back and look at the theorem very quickly, right? You need to go through k dimensions to get the effective rank big compared to n. K better not be too big compared to n. And then you want this other effective rank big compared to n. Okay, and if you think about that k star being, you can draw a bunch of conclusions. So the noise energy has to be distributed across lots of unimportant directions, which addresses your question in a very precise way. There have to be lots of non-zero eigenvalues. They should have a small sum compared to the sample size. And there should be lots of eigenvalues that are not much bigger than, this lambda k star, the point at which you cut off. So you need a sort of rather constant tail of many, many eigenvalues in the covariance in order to be able to hide the noise in those directions. And it's an if and only if. There are upper and lower bounds for that. Okay, and this is my second last slide. So yeah, so this terminology overfitting, I mean, these are cases where you're fitting perfectly. So there's no, I mean, over sounds pejorative, but you're certainly fitting the data perfectly, but it's benign overfitting. It's a very different thing from having bias too low and variance too high. It could be a very different thing. So for instance, if those conditions about the eigenvalues are satisfied, then fitting the data perfectly is totally fine in linear regression. If they're not satisfied, then indeed you're suffering from having variance too high. But they're different things. The fit to the data versus whether you're suffering from high bias, variance that's too high. I'll stop there. Questions?
For the last theorem, if your true theta is infinite dimensional and your all eigenvalues are positive, does the theorem imply that you can estimate true theta consistently?
So let me pull up the theorem.
If your true theta is infinite dimensional.
Yeah. There's nothing about dimension here actually. I mean, I don't think I was explicit on the first slide, but you can just be working in a Hilbert space.
Yeah, but I mean, if like all eigenvalues are positive, does the theorem say that you can estimate the true theta consistently?
That's right. This term is telling you the impact of the theta star transpose xi terms on the theta hat, and saying that the error that's caused by the distorted view that the sample covariance, if you want to think of it that way, gives you of theta star is not too bad as long as the trace, the sum of all those infinitely many eigenvalues, is dominated by n. Right?
Yes.
Does that answer your question?
I think what I mean is because your arrow, the excess arrow is like a norm between the estimated theta hat and the true theta.
Yes, that's right.
So if n is large, then basically it's saying that under
if 1 is large?
When n is large, when your sample size is large, basically saying that your theta hat is close to the true theta.
In the norm defined by sigma, that's right. So the sigma here those lambdas play two roles. One role is that they determine where the noise in the labels gets spread out among the parameter vector. Yep. And the other role they play is the one you're referring to, that actually the excess loss here is a measure of the error of your parameters, but it's weighted by those eigenvalues. So there are some directions with small eigenvalues that don't matter at all. Right? You can have big errors in those directions. And actually, this seems to be what the adversarial example story is all about, because you've got a direction with a huge amount of noise, right? Order n magnitude in that direction, but it doesn't matter at all.
So in the interest of time, let's take the rest of the questions offline, and we'll be back in about 17 minutes.